Hello, I'm Kashfia, and today I'm going to talk about geospatial biomass resource data acquisition and mapping. So in the year 2030, the United States will produce more than 320 million tons of organic residues. These kind of organic residues currently are being burned under open air or being dumped into the landfill sites, both of which have significantly negative impacts over the climate, environment, and the air quality. Instead of burning these residues, this could be used as a great resource to produce renewable energy. But to make a decision on where to locate a new facility, a power plant, a storage, or a new refinery like a biorefinery, it is extremely challenging. Because if we can't decide the best or optimal location for building a new facility, the transportation cost and associated transportation emission could pile up, and that will be an unsustainable solution. So I have been working with the Lawrence Berkeley National Lab and the Department of Energy's Joint Bioenergy Institute, where I collected the production data for different kinds of organic residues from thousands of resources from scratch. And then I aggregated those data in a format so that it can be displayed in a web-based interactive mapping tool called Biositing Tool. So what is a Biositing Tool? As earlier I mentioned that Biositing Tool will be a publicly available web-based interactive mapping tool, which will help the farmers to have access to information around the residue market where they can offer their crop leftovers. And it will also help the decision makers from the industry and the policymakers from the government to make the best decision on where to locate a new facility. First of all, I'd like to talk about the crop residue and how I collected those data. So I use the cropland data layer and the National Land Cover Database, both of which have millions of point location for different categories of crops. So, and this kind of point location are extremely spread out, and that's why I used unsupervised machine learning algorithm called K-means clustering. So what does the K-means clustering do? Basically, it takes those millions of point locations as input and creates clusters or zones as output. For instance, say one county has 5,000 point location where the corn is produced. Now, if I run the algorithm, it will give me the output of 20 different clusters, which has 20 centroids. So basically, in short, I aggregated 5,000 points into 20 points. And this kind of clustered centroids, after I generated those, I allocated the total amount of crop production into those centroids. And based on that, any decision maker can make a priority ranking and make the best decision on building a new facility. You can see from the pictures that there are the cluster centroids for different kind of crop categories, and in the web-based version, you can zoom in, zoom out, and can click on any of the points and see the production value for that specific cluster. So that will be helpful for the decision maker to make a decision. Next, I'll talk about how I collected the organic residue generated from the municipal solid waste data. So it was really hard for me, not because I had to run a lot of code, but because I had to collect data state by state. And firstly, I collected the county level data for different kinds of organic sources generated from MSW. Next, I got the shapes of different kinds of census tracts and allocated the total value of those organic residues in those census tracts based on the population proportion. So I used different kinds of moisture contents, residue factor, and finally got this kind of output. And if you look at the picture on the right, the larger the size of the bubble, the more production is available from that point location. So any decision maker, if they want to make a decision out of that, they can just use the point location and the size of the cluster. Next, moving on, I'll talk about the manual residue data collection. So firstly, I collected the data of the number of chickens, cattle, and swine. Then basically, I translated those numbers into manure using residue factors and moisture content. And finally, as I said earlier, if you look at this picture, the larger the size of the circle, the more production is available from that point. Again, that will be helpful for the decision maker to make the best decision. So working truly with big data and using a lot of like R, Python, JavaScript codes, it was a challenging thing, but at the same time very rewarding because I finally got to make some substantial and solid data products for LBL, and that will help the stakeholders to understand the economic opportunities and in terms of location and production value. And the challenges were data pre-processing and cleaning took a lot of time. Sometimes I didn't get data was unavailable, inaccessible, and then so yeah, that was like a time-consuming stuff. And data formats were different, structures was different, so aggregating data was hard. But at the end of the day, I'd like to say that getting the data into right shape seems it's really harder than how it appears to be in the first place. And data is only useful when it is presented in the right way. Thank you so much.
As you know, we're really awakening to the economic potential of bioresources, but they have so many uses in addition to bioenergy. Why they have, I think the tools you develop would be useful in all of those contexts.
Mm-hmm.
The source, these materials for all kinds of new processes, like soil amendment, like microbial production, microbial production. But why the focus on energy? Did that come from the project itself?
So yeah, JBA is responsible for bioenergy, so like they got the grant for that. But they are also interested on like other use of residues.
They do a lot of value-added processing for
It's
not about energy too.
Exactly. So yeah, it's a 3-year-long project. So they're also considering the fact of like incorporating those information as well in the mapping platform, because like it will be publicly available, so the public has the right to know that other than bioenergy use, how else it could be like used for other purposes.
It's one thing to use food residues, it's another to use crop residues. Are we concerned when you focus on crop residues that you are breaking the nitrogen cycle? This is the opportunity cost is soil fertility.
Mm-hmm. Yeah. So that is why that's why I did the K-means clustering, because like if a farmer can realize there is a market where they can sell their residues, they can choose that. And if they see that there is not enough supply of that specific category of crops, they might be like switching from like making like selling it off to the industry owners. Maybe they can use that for like manure, but like their fertilizer production, or like burn that and then like use that ash for even better purpose. Like that's also possible through seeing that clusters and then how much supply is available out of that. Yes.
How do they plan on marketing this tool? They're just going to put it on the internet and hope people know about it?
So I asked that question to my PI, and she said that it will be publicly available. So first, like anyone can access that, but to let the farmers know what will be their intervention. So according to her, like she said, like the Department of Energy has plans to work with the agricultural extension agents to let the farmers know that you can use this thing, and it's like highly interactive. You just have to like tap on a point and see that in which part of the county you are in, and they can just like use that.